Have you ever wondered what the biggest global threat to our health could be in the future? If the phrase multidrug-resistant bacteria isn't on your list, it should be. This term refers to bacterial infections that have evolved to withstand any known antibiotics, transforming into formidable foes in the battle for good health. In our world, antibiotics are often handed out like candy. They're frequently prescribed without much thought, and in many places, they're distributed without prescriptions like free samples at a supermarket. Even in factory farming, antibiotics are used not just to treat infections, but as a prophylactic measure to prevent them and enhance performance. But every action has a reaction, and in this case, the consequence is a steep rise in resistance. And not just any resistance, but resistance against our last line of defense, our reserve antibiotics. This overuse and misuse of antibiotics have led to the emergence of superbugs, bacteria that have essentially become invincible. This alarming reality underscores the urgency of developing innovative alternatives, new weapons in our arsenal to combat these resistant pathogens. It's a bit like being in a race against time, where the finish line keeps moving further away. But what if the answer lies within the problem itself? What if we can learn from these microbes, these bacteria, and use their strategies against them? That's the premise behind the research conducted by a team led by Yiyun Cheng at East China Normal University in Shanghai. They've turned their attention to lipoproteins, small protein molecules with fatty acid chains that bacteria use in their battles against microbial competitors. These lipoproteins have certain common factors. They carry a positive charge and an amphiphilic structure, meaning they have segments that repel fat and others that repel water. This allows them to bind to bacterial membranes and pierce through them to the interior. So, it seems we have a serious battle on our hands, but where there's a problem, there's always a solution. And the solution might come from an unexpected source, Fluorous lipopeptides. But we'll delve deeper into that in the next scene. To fight this battle, we might need to learn some tactics from the microbes themselves. You see, bacteria have their own little soldiers called lipoproteins. These are small protein molecules equipped with fatty acid chains, and they play a crucial role in bacteria's defense against their microbial competitors. Imagine lipoproteins as double agents. They have an amphiphilic structure, which means they are both hydrophilic, attracting water, and lipophilic, attracting fats. This dual character allows them to bind to bacterial membranes, sort of like a magnet attaching itself to a fridge, and then pierce through them to the interior, wreaking havoc from within. To make it even more fascinating, lipoproteins are not a new concept. In fact, several lipoproteins have already been approved for use as drugs. Just like how we humans learn from our enemies to build stronger defenses, scientists are taking notes from these bacterial warriors to develop innovative alternatives to traditional antibiotics. The key to lipoproteins' effectiveness lies in their positive charge and their amphiphilic structure. Think of them as having one foot in water and one in fat, allowing them to interact with both environments. With this ability, they can bind to the bacterial membranes, which are made up of both water-loving and fat-loving parts. Once attached, they can do their job of piercing through the membrane to the inside of the bacteria. Now, you might be wondering, how can we enhance this natural defense mechanism? Well, that's where the brilliance of science comes in. A research team led by Yiyun Cheng at East China Normal University in Shanghai is amplifying this effect by replacing hydrogen atoms in the lipid chain with fluorine atoms. This makes the lipid chain simultaneously water-repellent and fat-repellent, strengthening their binding to cell membranes and disrupting the cohesion of the membrane. Intriguing, isn't it? Now, let's see how scientists are enhancing this natural defense mechanism. Imagine if we could amplify the effect of these lipoproteins. Well, that's exactly what a research team led by Yiyun Cheng at East China Normal University in Shanghai set out to do. They had a unique approach, replacing hydrogen atoms in the lipid chain with fluorine atoms. Yes, you heard it right, fluorine atoms. So why fluorine? Well, it's all about the properties of this element. Fluorine atoms make the lipid chain simultaneously water-repellent or hydrophobic and fat-repellent or lipophobic. This unique combination allows the Fluorous lipopeptides to bind more strongly to bacterial membranes, piercing through them to the interior. The team synthesized a variety of these Fluorous lipopeptides, creating a whole spectrum of these potential antibiotic warriors. They used fluorinated hydrocarbons and peptide chains to create these compounds, linking them together with the amino acid cysteine. This formed a bond known as a disulfide bridge, ensuring the stability of these newly formed molecules. Now, you might be wondering why they chose to use fluorine in the first place. Well, fluorine's particularly low surface energy strengthens the binding of these molecules to cell membranes. At the same time, their lipophobicity, or fat-repelling nature, disrupts the cohesion of the membrane. In simpler terms, these Fluorous lipopeptides are like a double-edged sword. On one side, they bind to the bacteria, and on the other, they disrupt the very structure of the bacteria, leading to its downfall. They're not just a new class of antibiotics, they're a new class of super antibiotics, designed to tackle the toughest bacteria out there. They bind, they disrupt, and they conquer, all thanks to the power of fluorine. So we have these new weapons called Fluorous lipopeptides. But how effective are they? Well, let's dive into that in the next part of our journey. Now, let's see how these Fluorous lipopeptides fare against our adversary, the multidrug-resistant bacteria. The research team at East China Normal University in Shanghai began by synthesizing a spectrum of Fluorous lipopeptides. Imagine a vast library of these substances, each one a unique combination of fluorinated hydrocarbons and peptide chains. The amino acid cysteine was used as a sort of molecular glue, linking these two pieces together via a disulfide bridge, a strong covalent bond. With their substance library in place, the researchers then set about testing these molecules against a formidable opponent, methicillin-resistant Staphylococcus aureus, or MRSA. This strain of bacteria is particularly dangerous, resistant to nearly all known antibiotics. So how did our Fluorous lipopeptides do? Well, the results were quite promising. The team discovered one compound that outshone the rest. They named it R6F. Picture a Fluorous lipopeptide made of 6 arginine units and a lipid chain composed of 8 carbon and 13 fluorine atoms. This was the most effective compound against MRSA. But there's more to the story. To increase the biocompatibility of R6F, it was enclosed within phospholipid nanoparticles. Think of these nanoparticles as a protective shield, enhancing the Fluorous lipopeptide's ability to work within biological systems. In mouse models, these R6F nanoparticles proved to be highly effective against MRSA, tackling sepsis and chronic wound infections like seasoned warriors. What's more, no toxic side effects were observed. The initial testing process showed us that these Fluorous lipopeptides, specifically R6F, could be potential game changers in the fight against multidrug-resistant bacteria. But the question still remains: how exactly do these promising compounds work? So, we found a promising solution, but what exactly is it doing to these resistant bacteria? Let's delve into how these Fluorous lipopeptides are dealing the deadly blow to resistant bacteria. A fascinating aspect of these Fluorous lipopeptides is their multi-pronged attack strategy. Imagine them as tiny warriors armed with an array of weapons, each designed to target a different vulnerability of the bacterial enemy. First, they inhibit the synthesis of crucial cell wall components. Picture a castle under siege, with the enemy sabotaging the construction of its walls. As the walls crumble, the castle becomes more vulnerable, and so do the bacteria. But these clever warriors don't stop there. They also pierce the cell membrane, destabilizing it. Imagine a fortress with a breached gate. The defenses are compromised, and the invaders can now pour in. This is exactly what happens when the lipopeptides pierce the bacterial cell membrane. Simultaneously, these nanoparticles disrupt the bacteria's respiratory chain and metabolism. This is akin to cutting off the enemy's food and water supplies during a siege, leaving them weak and unable to fight back. And there's more. The Fluorous lipopeptides increase oxidative stress within the bacteria. Oxidative stress is like a fire within the bacteria, burning and damaging its structures. At the same time, these nanoparticles disrupt the bacteria's antioxidant defense system, leaving them helpless against the raging fire. The combined effects of these attacks are devastating for the bacteria. The Fluorous lipopeptides are like an unstoppable force, relentlessly attacking from all sides until the bacteria are defeated. What's truly remarkable is that this attack strategy works not just against MRSA, but other bacteria as well. Even better, there seems to be no sign of resistance developing against these nanoparticles. This is a game changer in the fight against multidrug-resistant bacteria. With these new insights, it's clear that Fluorous lipopeptides could be the future of fighting multidrug-resistant bacteria. It's not just about finding new weapons, but also about understanding how to use them effectively. And these Fluorous lipopeptides are proving to be quite the versatile and powerful weapon in our arsenal.